Hello everyone, today we will be learning speed control of induction machines. So before doing this lecture, uh, I'm assuming that you have already learned what the induction machine is, what the three-phase induction machine is. So I believe you know these formulas. For an example, uh, synchronous speed formula for induction motor and the slip for induction motor, slip is S, and also this formula which is induced EMF for induction motors and the per phase equivalent circuit for induction motors. Principle of control. So here you can see the equation for NS or synchronous speed. So it's equal to 60F. F here is applied frequency, normally it's 50 Hz, divided by P. P is pole pairs of the particular motor, of a particular motor. So if it's a 4-pole motor, pole pairs means 2 poles. You have to apply 2 here for 4-pole motor. If it's 6-pole motor, pole pairs means you have to apply 3 here. This is slip. So it's NS minus NR. NR is rotor speed. So NS, NR, all those are measured in RPM. So eliminating NS in this equation, we can prove that NR is equal to 60F into 1 minus S divided by P. So for a particular motor, you can say that P or the pole pair is constant, and for a particular loading, S is also a constant. So the only variable here is F. So in order to increase the rotor speed, we can increase F. If you want to decrease the rotor speed, we can decrease F. For an example, you have 50 Hz here. Let's say motor is operating 1400 RPM, and if you need to reduce it by 700 RPM, you have to reduce the frequency by 25 Hz, and you can run the motor in 700 RPM. Now here you can see the equation for induced EMF in a 3-phase induction motor. What is this induced EMF? Induced EMF is when you apply V1 voltage to induction motor, E1 is the voltage induced at rotor. This is stator. E1 is the voltage induced at rotor. So that is equal to 4.44 kW NPH F psi m. So if you take this equation, this one, that one, and this one, are constants. So only this E1, F and psi m are the variables. So in order to get the best possible torque per ampere, we need to keep psi as its rated value. So always the torque of the motor depends on psi. So you have to keep this one as its rated value. So using this equation, we can conclude that E1 divided by F1 is proportional to psi. And if we neglect the voltage drop across the stator, RS, this S is stator, XS stator, this R is rotor. So if we neglect this part, which means the voltage drop, neglecting voltage drop means you short circuit here to there. You can say that V1 is equal to E1. So V1 is this one, the voltage we apply to the stator. V1 is equal to E1. So you can modify this equation like this: psi is proportional to V1 divided by F1. To retain psi at its rated value, we should maintain the ratio V1 divided by F1 as at V1 rated divided by F1 rated. Now we will take an example. Let's assume for a particular motor, V1 rated is 100 volts and F1 rated is 50 Hertz. Let's assume for a particular loading, this motor is rotating at 1400 rpm, which means the rotor speed. So for 50 Hertz, the motor is rotating at 1400 rpm. Let's assume we need to run this motor at 700 rpm. So according to this equation, we have to maintain frequency at 25 Hertz. So to keep psi at its rated value, we need to apply voltage as 50 volts, because this ratio is 2, so 50 divided by 25 should also be 2. However, we should not take V1 above its rated value. This is the rated value of the motor, so we should not take V1 above its rated value of the motor. Therefore, above F1 rated, which means 50 in this case, we are forced to accept reduced psi, because beyond this point V by F is not equal to V1 rated divided by F1 rated. Motor torque is proportional to chi squared, and this makes torque fall squarely, but we do not have other choice. So in the induction motor lecture you have learned torque is proportional to chi squared. So here we know that chi is proportional to V by F, and V above F1 rated, we keep V as V1 rated and we increase this one, and what will happen, this will reduce and then torque will reduce. Now let's take an example. Let's say we need to operate the same motor at 2800 rpm. Rotor speed is 2800 rpm. So according to this equation, again for the particular loading, S is same, P is same, F is equal to 100 Hertz. So F is equal to 100 Hertz. Now we have to check the voltage. So according to this formula, we have to apply 200 volts, but that one is beyond this rated value, so we can't apply 200 volts. The maximum you can apply here is 100 volts. See, so this is the values of first example. This is the rated values, and this the 2800 rpm case. Practically we can't stick to ideal V1 divided by F1 condition and achieve constant flux down to 0 Hertz. We need to do voltage boosting at low frequencies to account for the stator resistance drop. So as you all know, we have neglected stator voltage drop in the previous slides. So if you take this one, we assumed V1 is equal to E1, and then we simplified the situation. But in the low frequencies you can't neglect this voltage drop, which is stator voltage drop. So in the low frequencies you can't stick to this V1 divided by F1 ratio. Since we need to account for stator voltage drop, we need to apply more voltage across the motor terminals. So this can be your V1 divided by F1 ratio, so it's a constant. So here you can see low frequencies. So what I do is, this is the applied voltage. I apply somewhat higher voltage here. For this point also I apply somewhat higher voltage. This point, this is the applied voltage. we apply somewhat higher voltage. The reason is to account for stator resistance drop, and then here you can get psi constant. So the curve is like this. So practically V by F, or V versus F curve is like this. For the calculation purposes, we can use this curve. Torque characteristics. Torque produced by the motor depends on the voltage and frequency combination applied to the motor. Now we know that torque is proportional to psi squared, and psi is proportional to V by F, so that we can conclude that torque is proportional to V squared by F squared. For the selected voltage and frequency plan, torque speed characteristics takes following shape. Here you can see various curves for a particular motor. This is called constant torque region, since maximum torque, or we say this one as pull out torque, is constant, and this is the constant power region. So pull out torque gradually reduces in the constant power region. We can take this one as the rated voltage and frequency. So beyond that point you have constant power region. Let's assume this is 50 Hz. So this is the torque speed characteristic. So you can run this motor in a lower speed, let's say 40 Hz. Now if you do not apply correct V by F value, you can't get this curve at 40 Hz. You may be getting something like this. Something like this, because you can't produce. If you do not apply correct V by F, you can't take this maximum torque, right? We need to try to get maximum torque from the motor. Rated voltage is applied in the constant power region. So we have discussed this one previously. Rated voltage is applied in the constant power region. We do not increase the voltage beyond this point. This is the rated voltage and frequency. This is the constant power region. Rated voltage is applied in the constant power region. We can increase current up to its rated value. So in this region, we know that motor is operating at V rated value, and you can apply I rated to the motor. V rated, I rated. So this is constant for a particular motor. Then V into I is also should be constant, which is power is constant. That is why this part is called constant power region. And if you take torque maximum into omega, that is also power. So torque maximum into omega is also a constant. So if you increase the speed little by little beyond this point, you will be getting this one reduced. Tm is called pull out torque, so hence the pull out torque gradually decreases when omega increases. Some important identities. Now we previously learned that induction motor has a constant torque region and constant power region. You can keep in mind these equations, no need to derive, and you can directly use these equations to your exam problems. Now if you concentrate on this constant torque region, torque maximum is proportional to V by F. So we keep V by F as constant. So torque M, or maximum torque or pull out torque, in this region is a constant value. You can assume these lines are parallel to each other, and these are straight lines. The gradient of these lines are V by F squared. Here you can see 50. If you take the voltage at this point as 400, so 400 by 50, there you can see 40, voltage may be 320 or whatever, and that one divided by this frequency, and 320 divided by 40, gradient squared, gradient should be same. And another important thing is, if you measure from pull out torque speed, pull out torque speed and synchronous speed, the distance between this pull out torque and the synchronous speed is same as if you take another graph, that's almost same, right? You can take that one as same value.